we're going to learn one more hypothesis test. And this is a hypothesis test for rho. So this is actually a lowercase r in the Greek alphabet, and you call this rho. And the idea of this is that when we've been calculating r, what I didn't tell you before is that r is actually the sample correlation coefficient. Okay, so it's the coefficient for a sample. And almost always when you calculate r, you're calculating it for a sample. Okay, but that sample is taken from a larger population, and if you actually did a census and gathered all the data for that population and you calculated the correlation coefficient for the entire population, we would call that rho. And it's a Greek letter. It looks like a P to me, but it's a lowercase r in the Greek alphabet. And so that represents the population correlation coefficient. And the idea here is we're going to use the strength of correlation in the sample to decide whether or not there's enough evidence to conclude a correlation in the entire population. Okay, so let me kind of give you an idea what could be going on here. Let's say your population had all these values and it was very large. Maybe there's more than these, but we'll just assume, okay, this is your population, and they're just randomly scattered, and you don't know that. You don't know if there's a correlation in the population, okay? But in this case, if they were randomly scattered and there was no correlation, rho would equal 0, right? Because 0 means that there's no correlation. And then let's say you went there and you took a sample of 5 values. Let's say you grabbed that one, you got that one, this one, that one, and we'll say this one. And let's say those were the values that you actually sampled. So all the other ones went away and you did a scatter plot with just those 5 values. Well, in that case, R here, R suggests a strong positive correlation, doesn't it? And in this case, you would be wrong because there's actually no correlation in the population. Okay, you just happened to pick 5 values by chance that had a pretty strong positive correlation. Okay, so this test is kind of testing to see whether or not the correlation in a sample provides enough evidence to conclude a correlation in the population. Okay, because your sample could have a correlation and the population might not. And so this is a test that you would use to decide that. So the book actually has 2 different tests. One's a test that uses the t-table, and it's a really nice test because you can actually test whether or not the strength of the correlation is like greater than 0.8 or greater than 0.9. There's a lot of versatility, but this test, there's absolutely no versatility at all, but it's very, very simple. That actually makes the test very easy to do. Okay, you use this table, and as you can see here, H naught here is just rho equals 0. So the null hypothesis here, so let me actually write some information that we're going to need here. So let's say I take a sample of 8 values, and when I do, of a population, when I do, my R is negative 0.814, and I'm going to test this at alpha equals 0.05. Okay? Now, whenever you perform this particular test, H naught will always be, there is no correlation. rho is equal to 0, right? No correlation. And then you want to test, no, I think that there is a correlation. Okay? Now this is negative, but don't say, no, I think rho is less than 0. Okay? Because we don't know R before we set up our test, right? And so R is unknown. And if you look at this table, it says that the values on the table are for a two-tailed test. And so this will always be, no, I think rho is not equal to 0. And this would be that there is a correlation. So those are the two decisions. The null hypothesis just assumes nope, there's no correlation, no relationship, and and H, the alternative is no, I think that there is a correlation. There is some correlation, or at least rho is not equal to 0. So this test is actually just going to be testing to see that rho is not equal to 0. Okay? So the nice thing about this test is because this is a two-tailed test and H naught is always rho equals 0, this is always going to be the hypothesis. It's always going to be that. This will always be H naught rho is equal to 0, H1 rho is not equal to 0. And it'll always be a two-tailed test. Now, when you determine the rejection region, I just draw a curve here. Okay, now this test you'll find, this particular table, you'll find that it's on Canvas underneath these videos on the home page. And you can see that this is a very simple table. It only has two significance levels, 0.05 and 0.01. Those are the only two significance levels. And then notice also that the degree of freedom, so these are the degrees of freedom, the degree of freedom is n minus 2. Okay, so we're going to do this at alpha equals 0.05. Ooh. Let's see here. It's a little blurry. Let's see if I can get it to focus a little better. There we go. So I'm going to do it at alpha equals 0.05. My degree of freedom is going to be 8 minus 2. So my degree of freedom is going to be 6. And so you might want to make a little note here that says the degree of freedom is equal to n minus 2 when you use this particular table. So this is a two-tailed test. Okay, and you're going to go to alpha equals 0.05, 6 degrees of freedom, and you get this particular critical value. It's 0.707. So this is negative 0.707. This is 0.707. Now notice these are not critical z-scores anymore. So these are, you can think of these as critical R scores if you want to. We're going to compare, the test statistic is actually going to be R itself, and you're going to compare it to these values here. Okay, so this side would be reject H naught, and this side over here would be reject H naught, and then in the middle is fail to reject H naught. And notice by rejecting H naught, we're not rejecting that there's a correlation. H naught says there's no correlation. So in order to show a correlation, we have to have enough evidence to reject H naught in favor of the alternative that says that there is some correlation. Okay? So that will be my rejection region. So the test statistic is R. Okay, and in this case we're told that R is negative 0.814. And so that actually does lie in the rejection region. Okay, and so we would reject H naught. So my decision is reject H naught. And whenever you reject H naught, that means there is enough evidence to conclude the alternative. And in this case, the alternative is always that there's a correlation. Okay, so there is enough evidence to conclude a correlation. And that's the end of the test. Okay, now notice this does not tell us how much correlation there is. It's just testing that we have enough evidence to conclude that R is not equal to 0. So there is at least some correlation. And so in that sense, it's kind of not the greatest test. It's better if you can test to see if like rho is greater than 0.8 or something like that. And then you're actually testing for a certain amount of strength in your correlation. And you can do that, but it is a different test. And it's a test that uses the t-table and a test statistic and all that. And you can read about that in the book, but we're not going to do that. This is the only test we're going to do. Okay? And I want you to actually write out the steps here because I want you to see that you can do hypothesis tests with things other than mu, with something other than the population mean. Okay? In this case, we're testing for population, the correlation coefficient in the population. So there's many different hypothesis tests for different for different measures. Okay, and so you can do things. You can test for more than just the mean. So I'm going to do one more here, and then I'm going to want you to try one here. Okay, so for this one, we'll say n is equal to 65, and sorry, let's let n be equal to 35. I'm going to rewrite this. Let's say n is equal to 35. R is equal to a positive 0.432, and we want to test this at alpha equals 0.01. Okay, so remember the null will always say that rho is equal to 0. There is no correlation, and the alternative will always be rho is not equal to 0. There is at least some correlation. Okay, so then my rejection region, my alpha is 0.01, the degree of freedom is 35 minus 2, which is 33. Okay, now when you look at this table, and this is one reason for doing this one, you can see that the degrees of freedom go up by 1s until you get to 20, and then they go up by 5s until you get to 50, and then after that they go up by 10s. So a degree of freedom of 33 here. Okay, now 33 is closer to 35, but what you're going to do is you're always going to pick the largest degree of freedom that's less than your actual degree of freedom. So for 33, I'm not going to go to 35, I'm going to go to 30, and then I'm going to go to 0.01 for my significance level. So what I get here is 0.449. Okay, so the principle here is you're going to go to the largest one on the table that's less than the actual degree of freedom that you have. And in this case, For degree of freedom 30, alpha 0.01, we got 0.449, and this would be negative 0.449. Okay, and so this is like reject H naught. Over here is reject H naught. And in the middle is fail to reject H naught. And my test statistic actually lies in the middle. Okay? And so what that means is I'm going to and my test statistic is R, remember, 0.432. And so that means I'm going to fail to reject H naught, and that means there is not enough evidence to conclude a correlation. So there's not enough evidence to conclude a correlation in this case. So one thing I want you to notice is that the way this works, right, if your R is close to 0, right, then that means the correlation in your sample is very, very weak, right? You wouldn't have any evidence to conclude a correlation. So the closer R is to -1 or to 1, the more evidence you would have to conclude a correlation. And this number on the table is kind of your cutoff, that critical value. In other words, it either has to be below a negative 0.449 or above a positive 0.449, right? It has to be closer to -1 and 1 than the plus minus 0.449. Okay, so in a sense, you can kind of just look up this on the table and think of your R value and know that, oh, yep, my R value is closer to 1 or -1 than this particular value on the table. Okay, so it's actually a very easy test to do. But I do want you to do these 5 steps of a hypothesis test, because then it shows you that these 5 steps, basically you got all kinds of different hypothesis tests for things other than the mean, and they all involve those same 5 steps. It's just that there's, different, a different symbol for what you're testing, row in this case, different table maybe to get your critical values. Your test statistic is different, but then you make your decision and interpret the results, and it's all very similar from test to test. What changes really is, depending on what you're testing, where you get your critical values and how you calculate your test statistic. Okay, so now to finish this up, we calculated R here for the hours in the GPA. This is the number of hours they work in their GPA, and we saw that there was a very strong negative correlation. So what I want you to do in a minute is pause the video and perform the hypothesis test. Write out all 5 steps and test to see if there's enough evidence to conclude a correlation in the entire population. So go ahead, press pause. When you're done, you can resume the video and see how you did. Okay, so let's go ahead and give this a try. So, oh, you know what? I did not give you a critical value, did I? I meant to say test at alpha equals 0.05. If you want to pause, if you didn't know what to do there, you can pause and start it up again, or maybe you just check both of them, because in this case I think you're going to reject it at both significance levels. Okay, so it wouldn't have mattered. Let me make sure I just told you the right thing. No, you almost make it, but you just don't quite make it. So we're going to test it at alpha equals 0.05. For the 0.01, you actually are very, very slightly off. So let's test this at alpha equals 0.05. So my null says that there is no correlation. Rho is equal to 0. My alternative says that rho is not equal to 0. And then my degree of freedom here is 5 minus 2, which is 3. And so if I go to my table, I go to 0.05, 3 degrees of freedom, I get 0.878. So this would be 0.878. This would be negative 0.878. Okay, and so over here and over there would be reject H naught. So step 3, this is your test statistic, and it's 0.957. And step 4, 0.957 is over here, so you would reject H naught. And this is what I was saying, if it was at the 0.05 significance level, or if it was at the 0.01 significance level, you would have 0.959, and it would just almost, it would be really, really close, but it wouldn't quite be in the rejection region. Okay? But at the 0.05 significance level, there's enough evidence to reject H naught, and that means there is enough evidence to conclude a correlation. So you have enough evidence to conclude a correlation in this case. Okay, and that's good, because what we're going to learn here in the second half of chapter 10 is how to determine the regression line. And this is like the line of best fit, the line that kind of fits the data the best. The regression line kind of goes through the data, and it fits the data the best, and that can be useful. In this particular example, you're going to see why a regression line might be helpful. But first we have to learn how to calculate the regression line, and one of the rules is you don't use a regression line unless you have enough evidence to conclude a correlation. Okay, because if there's no correlation, then a regression line is not helpful. It wouldn't give you valid results. So you always want to be able to pass this test before you conclude a correlation, or before you determine the regression line. And that's what we're going to do in the second half of chapter 10.